Welcome everyone. Today we'll be solving a problem for all the animal herders out there. Suppose you have a cow that is tied to a circular silo at some point, and its rope is the length of half the circle's circumference, meaning the cow can go halfway around the silo before it can go any further. The question is simple. What is the area available for grazing by this cow? Well, let us find out. I'm going to show a physical demonstration of this problem so you can get some intuition about it. First, notice how when the cow moves away from the silo, the farthest it can go is the entire length of its rope, as the rope is not being hindered by the silo. The cow can do this for 180 degrees. Hence, in those 180 degrees, its farthest grazing distance traces out a semicircle. Second, if the cow moves around the silo, notice how its rope pulls around it, and the farthest distance the cow can go becomes shorter than the length of the rope. You can see that the rope is being pulled taut until a certain point. Then the rope becomes a straight line segment tangent to that point. This distance will be shorter by part of the silo's arc length, and to go that distance, the cow will point in a direction the same as the tangent line segment. So we get this intuition of how the curve looks like. Moving away from the silo, the cow is not restricted and can move around in a semicircle, and moving towards or around the silo, the cow is restricted, and so its distance away from it gets shorter and shorter. So as you saw in the animation, the right part of the cow's grazing area is the area of a semicircle whose radius is the length of the cow's rope, and here it is very simply calculated with the formula for area of a semicircle. But the real challenge is figuring out the area under the curve which describes the cow's path as it moves around the silo. And we are going to do this using parameters. We're going to describe such a curve parametrically, and then to find its area, we simply have to integrate over it. Let's think back to the animation and to what the curve looks like. So the cow here is going around and around the silo. Its rope is getting tighter and tighter around it until at a certain point, say here, the rope stops being tightened and the cow goes in a straight direction until the length of its rope runs out at another point there. Now I'm going to label these points. First, I'm going to draw some coordinate axes through the center of our silo. This is going to be the y and the x, respectively. And so we can now label our points in the Cartesian plane. This first one where the rope releases, I will call PQ. And this one where it ends, I will call MN. So notice something about PQ. If we draw a line to the center of our circle, which is now the origin conveniently, we can call this angle theta, and hence PQ will simply be cosine, or r cosine of theta, and r sine of theta. So that's our first thing we can write out. P as r cosine of theta, and Q as r sine of theta. Now our goal becomes quite clear. Notice that for any theta rotating from 0 to pi radians, this will always hold true. There will be this P and Q, which will be r cosine of theta, r sine of theta, and there will be some M and N, which will describe the end of our rope. And so if we can express M and N in terms of theta, or as a function of theta, then we would successfully have parametrized the curve that the end of the cow's rope traces out as theta ranges from 0 to pi. And so we would be able to move on to integration. To do this, we have to remember a formula. Recall that x minus a all times a plus y minus b all times b equals 0 is the equation of a line tangent to a circle at point AB. We can derive this equation very easily using implicit derivatives, and here's the outline for it on screen if you want to know. Now, why is this useful? Well, notice at the point PQ, the cow's rope streams off in the direction of the tangent line. Therefore, point MN sits on that tangent line. And so we can set up a very nice equation to solve for M and N. Let us now write the equation of the tangent line at PQ to the circle is going to be x minus p times p plus y minus q times q equal to 0. This is the tangent line. We can set up two equations about Mn. First, we know that Mn belongs to the tangent line. So m minus p times p plus n minus q times q equals 0. And second, we know that the distance between mn and pq is going to equal a certain value. Well, what is it going to equal? Well, simply the length of the rope, pi r, minus this arc right here of the circle. And what is this arc equal to? Well, conveniently, since we set this angle here to theta, this arc simply is measured by r theta, right? We all remember that formula. So we get that the distance, using the distance formula, the square root of m minus p squared, then plus n minus q squared, the distance between them, is equal to the length of the rope, pi r, minus this circular segment, which is r theta. How nice! We have two equations, and using these, we can actually solve for m and n in terms of theta. So let's do that. Clearly, this equation will have two solutions because we're asking about the distance from a certain point on a line. So say this is a line with the point PQ, and we are asking about the points that satisfy some distance requirements. So there will be two of them on either side of the line. This is solution 1, and this is solution 2. So after we solve this equation, we will have to choose which one fits our necessities. And how do we solve this equation? Well, we can use a very clever trick of substitution. From our first equation, we can say that m minus p times p is equal to negative n minus q times q. And therefore, m minus p is equal to negative n minus q, and then times q over p. And what is q over p? It's simply r sine of theta over r cosine of theta, the tangent of theta. So this is what m minus p is equal to, and we can substitute this value of m minus p into this square root. And notice what we get. Square root of n minus q squared, then plus m minus p squared, which is equal to this whole thing squared. So n minus q squared, and then times the tangent of theta squared. This is equal to r times pi minus theta. And so we can take out the n minus q term out of here and get that n minus q, and then times the square root of tangent square root of theta plus 1, which is equal to the absolute value, I'll write it here, the absolute value of n minus q times, recall that this is simply inside the square root is the secant squared of theta by the Pythagorean identity. Therefore, the square root of it is the secant of theta. And since we are taking stuff out of the square root, we have to put absolute value bars around the entire expression. And so the absolute value of this is equal to r times pi minus theta. We can perform a very similar substitution for n minus q using m minus p, and we get the other equation that the absolute value of m minus p times the cosecant of theta is equal to r times pi minus theta. To solve these equations, we can avoid the absolute value bars by squaring both sides. And so we get that n minus q squared, and then times the secant of theta squared is equal to r squared times pi minus theta squared. And remember, we are solving for n, so we want to isolate it. Then we can simply divide everything by secant squared to get that n minus q squared is equal to this over the secant squared. So r squared pi minus theta squared over secant squared of theta. And so we can take the square root of both sides, getting rid of the squares, but we now have to put a mandatory plus or minus sign. Remember what I said about the two solutions. So we finally get, by taking the square root of both sides, adding the plus or minus, then carrying over the q, that n is equal to plus or minus r times the cosine of theta, all times pi minus theta, plus q. Remember, dividing by a secant leaves us a cosine in the product. Now note that the q at the end can be changed into an r sine of theta, so n is equal to plus or minus r cosine of theta times pi minus theta plus r sine of theta. And we can do basically the same process to get m out of this equation in the absolute value. And here the cosine and the sine are just swapped. So we get that m is equal to plus or minus r sine of theta times pi minus theta, and then plus r cosine of theta. Just like that. We have almost found what m and n are. We now just have to decide what signs to give them so that they fit our criteria of the cow going around the semicircle. The best way, I think, to test this is through some simple case work. So follow with me here. Note that if theta is in the first quadrant, so if theta is between 0 and pi over 2, then what will we want of our point Mn in regards to PQ? Well, note that since the cow is going around this way, Mn will have to be above PQ and also to the left of it. So writing out that in our inequalities, we get that this implies that the x-coordinate m is less than or equal to the x-coordinate p of this point, and p is of course our cosine of theta. And for n, we get that n has to be greater than or equal to q, which is our sine of theta. Noting that p minus theta is positive, we can very easily tell which one of our two options for m satisfies this criteria. Since there is an r cosine of term here, we want this r sine of theta term to be negative. I'm going to write this in a slightly strange notation. Just follow with me here that m colon negative. This means we're choosing a negative sign in here for the value of m. Now for n to be greater than or equal to q, the story is very similar. Note the positive coefficient here and the r sine of theta here. And since we want to be greater, we have to choose the positive sign for n right here. So n colon positive. Okay, now for the second case where theta is between pi over 2 and pi, remember those are our only values of theta since the calc cannot go any further. So I'll write it down. When pi over 2 is less than or equal to theta is less than or equal to pi. What does that again say about our point Mn? Well, now it will be less than PQ. It will be below PQ, sorry, and also to the left of it. And again, writing that in our language, we get that M should be less than or equal to P, which is our cosine of theta, and N now will be less than or equal to Q instead of greater, which is equal to our sine of theta. For m to be less than or equal to p, the reason is identical to that of the first quadrant, so m we have to choose the negative one. And now for n to be less than or equal to q, first note that cosine of theta in the second quadrant is negative. Therefore, if we have a plus sign here, then this whole term with the cosine of theta will be a large negative number. And so adding it to our sine of theta makes it less than our sine of theta. Therefore, we have to choose the positive sign for n, like this. And just like this, we have successfully parametrized our curve that the cow makes when it walks around the silo. Now we can finally move on to integrating to find the area. Now we can finally connect the pieces to get an expression for the grazing area of this cow. First, we take the area of this semicircle, which we already computed. Then we take the area under this parametric curve, as you saw in the animation. Then we have to double the area of that parametric curve, because remember the cow can also go around in this way below, as well as this way for which we are computing. And then we have to subtract the area of this entire silo, because when taking the area under the curve, it is also bound by the x-axis, so we will have this unnecessary part of the circle here. So combining all of that, we get the area, which I will call A, to be first 1/2 pi cubed r squared. Then removing the circle, we get minus pi r squared. And then we add twice the integral from pi to 0, because again, we're going to the right of, remember the parametric integration theorem, we have r cosine of theta times pi minus theta plus r sine of theta. And this is all times the derivative of this, of, I'll have to write it a couple spaces down, of minus r sine of theta times pi minus theta plus r cosine of theta, all in brackets and multiplied, and d theta. So this is going to be our area. Now, this isn't a particularly hard integral. There's just like 10 integrals in here. So if I were to simplify all of this right here in the video, it would take at least 10 minutes. So I'm not going to do that. I'll have some pages on screen if you want to check my algebra for some reason, but most people will do this with a computer algebra system anyway. And so we can simplify this result to the very nice 5/6 of pi cubed times r squared. And this is the final answer for our problem. The grazing area of the cow tied to a silo with a radius of r is this 5/6 pi cubed times r squared. So that is it for today's video. Thank you all for watching this exercise in parametric calculus. I hope you all enjoyed it as much as I did. I think this curve looks really cool, and paired with the semicircle, it kind of looks like a cardioid, although it's not exactly a cardioid. And yeah, as I said, that is it. Thank you all for watching. I greatly appreciate it, and I will see you in the next one.